Hi, welcome to the video module on frequency dependence of permittivity. In this video module, we will discuss about electromagnetic waves in non-conducting, conducting, and plasma medium. In many of the previous modules, we learned about electromagnetic waves through the propagation of electromagnetic waves through matter, and is governed by mainly three important properties of the material. They are permittivity, permeability, and conductivity. Actually, these parameters depend to some extent on frequency of the waves which are propagating. We know that refractive index of a medium refractive index of a medium is approximately equal to square root of the relative permittivity or dielectric constant of the medium, root of epsilon r. If we consider permittivity as constant, then that shows the refractive index also constant. But in reality, it is not like that. We all know that refractive index of a medium, refractive index actually depends on wavelength of light. Refractive index depends on wavelength of light. You can see the variation of refractive index with wavelength. See, for 4000, it comes up to 1.48. So how it changes when the wavelength increases? That means refractive index changes with wavelength. So if refractive index changes, then there will be change in the relative permittivity also. There are many practical examples for this dependence of refractive index on wavelength. The well-known examples of rainbow or the case of a prism are due to the variation of refractive index with wavelength. We all know that when white light, a, a composite light, a white light is allowed to pass through a prism, different colors bend to different extent because different colors has got different wavelength. So the refractive index also different. As the refractive index is different, the bending also different. We all know that violet color bend to the maximum and red to the least. Based on this, we'll get a spectrum of colors on the other side of the prism. This phenomenon of splitting of a composite light into its component colors is known as dispersion. And the medium is known as a dispersive medium. So what is actually the reason for dispersion? The reason for dispersion is the different travel speeds of various frequency or various wavelength in a medium. Different waves travel at different speeds through a medium. That is because of the variation of refractive index, because speed of a wave in a medium depends on its refractive index. What is the actual expression for refractive index? It is a ratio of speed of light in vacuum to speed of light in medium. We all know n equal to c over v. So as the refractive index depends on wavelength, the speed also depends. So different colors travel at different speeds through the medium, through a dispersive medium. Because waves of different frequency travel at different speeds, the shape of the wave actually changes. because we can consider the propagation of a light beam as a combination of a number of frequencies. So as all these frequencies travel at different speeds, their shape changes when it travels through a medium. So here you can see one particular component wave that is shown in blue color here. Okay, this is one particular component wave traveling through a medium, and the speed of that wave, the speed with which one particular frequency wave travels through a medium, is called its phase velocity or its wave velocity, velocity of that particular wave only. And it is given by V equal to omega divided by k, where omega is the frequency of the wave and k is the wave vector. So if a number of waves having different frequencies are there, then altogether, or we can say the wave packet, altogether this wave packet travels with a speed called group velocity, which is given by Vg equal to d omega by dk. So I hope it is clear. When a number of waves travel through a medium, the speed with which each frequency waves travel is known as phase velocity or wave velocity, and the speed with which the total wave or all waves as such moves, it is known as the group velocity of the waves. So we discussed about frequency dependence of or wavelength dependence of refractive index, through that the wavelength dependence of permittivity. And also we discuss about group velocity and wave velocity. You can see the component waves and the group or the wave packet as such moving with a different velocity called group velocity. So in this video module, actually we are going to discuss about the dispersion in dielectrics, in conducting medium and plasma medium. So um, we learned about propagation of electromagnetic waves in non-conductors, conductors, etc. But there we considered the relative permittivity of the medium as constant. But actually, with the help of the prism, the case of prism, we proved that relative permittivity is actually not a constant. It depends on the wavelength. It depends on the frequency of the wave. So we'll discuss this in detail. So first, dispersion of electromagnetic wave in non-conducting medium. What is a non-conducting medium or a dielectric medium? We know that in a dielectric medium, the electrons in a dielectric medium are actually bound electrons. They're not free electrons as in the case of a conductor. They're bound electrons. Bound means they're bound to the nucleus. They cannot move away. They're not free to move around. They are bound to the nucleus. Um, they're tied to the nucleus. We can say like that. So in order to visualize this, it is better to take the electron attached to the nucleus with the help with a string or something. We can say a spring. An analogous situation. It can move around its own fixed positions. It cannot move freely from the position. So an electron attached with to the nucleus with a spring is a best analog to the situation in the case of a non-conducting medium. So you can see here this analogous situation of electron attached to the nucleus with the help of a binding force. So in order to analyze the situation, we are imagining that electrons are attached to the nucleus with the help of a spring with a spring constant k spring. So this electron can oscillate about its own mean position or equilibrium position. They cannot move freely from there. They can move if this is the equilibrium position. They can move about this equilibrium position like this. So it constitutes a wave, a sinusoidal wave, just like the case of a spring, a simple harmonic motion. So what is the binding force? So as we consider the case analogous to a material attached to another one with the help of a spring, we can take the Hooke's law. We can take Hooke's law for representing the force that binds this material, this electron, with the nucleus. So what is the binding force? We know that the binding force is given by F is equal to negative kx. Here the k spring times x. X is the displacement from mean position. What is k spring? K spring is equivalent to omega 0 square times m, or m omega square. So plug that value m omega square here, m omega 0 square here. We get the binding force is equal to minus m omega 0 square x, where omega 0 is the natural frequency of oscillation. It is given by omega 0 equal to square root of k spring divided by m. So this gives the natural oscillation frequency. And there will be a damping force also, which is given by F damping is equal to negative m gamma dx by dt. Gamma, the damping coefficient or damping constant. What makes this electron to oscillate? So when an electromagnetic wave enter the non-conducting medium, the electromagnetic wave of frequency omega enter the non-conducting medium, it makes the electron to oscillate. So the driving force here for the electron to oscillate is provided by the electromagnetic field or the electric field of the electromagnetic wave. Because we know that electromagnetic waves consist of electric field as well as magnetic field. So if electron of charge Q is subjected to an electric field E, then the driving force is given by F driving equal to QE, where E is a sinusoidally varying electric field is Q times E0 times cos omega t. What is this omega? This omega is the frequency of the electromagnetic wave that enter into this non-conducting medium. So F driving is equal to QE0 cos omega t. Now, so what are the total force on it? Or we can apply Newton's second law. What is Newton's second law? F is equal to m times A, or which is d square x divided by dt square. So F is equal to the total force. F is equal to m d square x by dt square. So that is F total. Actually, what are the forces acting? The binding force, the damping force, the driving force. The three forces are there. This gives a total force on that. So F total is equal to F binding plus F damping plus F driving. Now we can substitute the expressions for all these forces and rearrange this. So what you will get is m d square x by dt square equal to negative m omega 0 square x plus, sorry, this minus m gamma dx by dt plus QE0 cos omega t. Now rearranging the two negative terms to the left, we'll get m d square x by dt square plus m gamma dx by dt plus m omega 0 square x equal to QE0 cos omega t. Here omega 0 is the oscillation frequency and omega is the frequency of electromagnetic wave enter into the non-conducting medium. Now slight rearrangement again. Take the m as a common factor from the right side and you can write it as d square x divided by dt square plus gamma dx divided by dt plus omega 0 square x equal to q divided by m E0 cos omega t. Now, in order to make this calculation simpler, or for the simplifying the calculation, we can consider this expression. We can consider this expression as the real part of a complex equation. It will be always easier to solve this equation if we consider this as the real part of a complex equation. So we can write this expression as d square x by dt square x tilde plus gamma d by dt of x tilde plus omega 0 square x tilde equal to q by m e0 e x mine e to the power minus I omega t. Here you can see here x tilde or x bar or x tilde is actually the complex function. So d square by dt square of x tilde plus gamma d by dt of x tilde plus omega 0 square x tilde is equal to q by m e0 e to the power minus I omega t. And the real part of this equation is the expression that we already wrote there. So the system oscillates with a driving frequency omega. So the solution to this equation is of the form x tilde equal to x0 e to the power minus I omega t. And when we insert this into this expression and simplify, we'll get the value of x tilde as x0 tilde as q divided by m omega 0 square minus omega square minus I gamma omega E0. How? Let us see how this expression is obtained. So let us find d square by dt square x and d by dt of x. So what is d square, or what is actually d by dt? Let me see. Okay. What is d by dt of x tilde? It's a complex notation. That is d by dt of x0 e to the power minus I omega t. x0 tilde is constant. Then exponential, the differential of e, exponential is the same quantity. So e to the power minus I omega t. Then a minus I omega also will come, minus I omega. So this is the value of d by dt of x. Now again differentiating d square x by dt square, what you will get is x0 bar is already there. Then exponential minus I omega t is there. Then again one more minus I omega will come. So minus I omega. What is the answer here? x0 tilde e to the power minus I omega t. Then there is minus into minus, it becomes plus. But there is I and I again. So I times I, it is minus 1. So a minus will come here. Then omega times omega, omega square will come. Okay, now we can plug all these into the expression. What you will get is the first one become minus x0 bar omega square e to the power minus I omega t minus gamma x0 tilde I omega e to the power minus I omega t plus omega 0 square x. Again x tilde can be replaced by x0 tilde e to the power minus I omega t equal to the term on the right side, that is q divided by m e0 e to the power I omega t. So you can see the e to the power I omega t is a constant term on right side as well as on left side. I mean, is the term appears in each term, so we can take that out and cancel. So what is remaining is minus x0 tilde omega square minus I gamma x0 tilde omega plus omega 0 square x0 tilde equal to q divided by m E0. Okay. Now x0 tilde is a common factor. So x0 tilde equal to, you can rearrange omega 0 square is plus. So I can write that first, omega 0 square minus omega square minus I gamma omega equal to q divided by m into E0. Okay. Now take the bracket term to right side. It will be x0 tilde equal to q by m divided by omega 0 square minus omega square minus I gamma omega times E0. What is this omega 0? It's the oscillation frequency. What is omega? It's a driving frequency or the frequency of the electromagnetic wave. Gamma is the damping constant. Q and M are the parameters of electron. So we got the displacement of electron from its mean position, the complex displacement, I mean. So how do you find the dipole moment? We know the dipole moment is charge times displacement. So we can write the dipole moment as the real part of the complex dipole moment, q times x tilde. This is q times charge times distance. Charge times distance is dipole moment. Okay. So q times x. You already know what is x0, right? So q square, q times q, one q already there. So that is why q square divided by m divided by omega 0 square minus omega square minus I gamma omega E0 e to the power minus I omega t. Why? I'll write this if you have confusion. So P complex equal to Q x complex. That is Q times what is x complex? It is x0 complex e to the power minus I omega t. For this x0 complex, we substituted the box term here. Okay. So from there, we get P complex equal to q square by m divided by omega 0 square minus omega square minus I gamma omega E0 times exponential minus I omega t. So what we got here, the complex the dipole moment. This is about a single electron. But we know that a molecule consists of a large number of electrons. And different electrons experience different natural frequencies and damping coefficients, not identical every time. Okay, so we got an expression for complex dipole moment of a single electron oscillation due to the driving force provided by an external electromagnetic wave. But we know that a molecule consists of a number of electrons. All this they might have a different natural frequencies omega 0 and damping coefficient gamma. So for one omega 0 1 omega 0 2 like that. So one or two or three or like that, a number of electrons in a molecule may have same natural oscillation frequencies. Okay, for example, if a if an electron consists of 10 electrons, okay, 3 of them having one natural frequency omega 0 1, 4 of them having another natural frequency omega 0 2, 2 of them having another natural frequency omega 0 3, and one of them having another natural frequency omega 0 4. So how to generalize this? So in a molecule, if fj number of electrons are having a particular natural frequency omega j, instead of omega 0 we are representing omega j, the natural frequency of j number of electrons. I hope it is clear. An electron, a molecule consists of a number of electrons, and each electrons, the natural frequency and damping coefficient of each electron are not, they may not be the same, but there can be a group of electrons having same natural frequency and the same damping coefficient. So let us say fj number of electrons in a molecule having same natural frequency omega j and damping coefficient gamma j. So now how can we write the dipole moment of such a so if fj, so how to find the total dipole moment? There are fj1s. Fj values can be varied, right? J number for one particular, j another number, so we can sum over all j's. Okay, so that is why the total, the dipole moment is given by q square divided by m. Q square divided by m, then sigma sigma over j, fj divided by omega j square minus omega square minus I gamma omega E complex. Instead of writing E0 e to the power I omega t, we wrote E complex here. Okay, that is why this sigma notation came. Now, if the if there are n molecules, what we discussed here is about one molecule and the electrons inside that. Now, if there are n molecules per unit volume, then what is the polarization of the sample? How you write polarization, dipole moment per unit volume? The polarization of the sample is given by P. This is small letter p here is. This is capital P. So, if there are n molecules per unit volume, then the total dipole moment per unit volume is given by P, capital P tilde is equal to nq square by m sigma fj divided by omega j square minus omega square minus I gamma omega times E complex or E tilde. Okay. Now we already learned that polarization is E epsilon 0 chi E E, the permittivity of free space, susceptibility, electric field. In terms of complex notation, P complex equal to epsilon 0 chi E complex E complex. Where chi E complex, chi E tilde is the complex susceptibility. It is related to the complex permittivity with the relation epsilon complex, epsilon tilde equal to epsilon 0 times 1 plus chi E tilde. So now we can write the expression for we already know the expression for epsilon, or we can compare this expression to get this epsilon r value. So let us compare the two expressions that we have now. One is polarization and the same expression for polarization this way. So when you compare this, you can see that the left side, it is polarization P here and here. Okay. And on the right side, you can see the E complex here and E complex here. So what you can write is epsilon 0 chi tilde equal to n q square divided by m, then the complete term inside bracket is fj divided by omega j square minus omega square minus I gamma j omega. So what is chi from this expression? Or we can, yeah, epsilon 0 chi is there. Now we can plug the same in this epsilon complex expression. This can be written as epsilon 0 plus epsilon 0 chi complex. Okay, that can be written as epsilon 0 plus epsilon 0 chi. Instead of epsilon 0 chi, you can write, what is that? N q square divided by m times the bracketed term there. Okay. So how do you find epsilon r now? The relative permittivity. We know that epsilon r equal to epsilon divided by epsilon 0. So epsilon r complex. So epsilon r tilde is equal to, when you divide this, the first term epsilon 0 divided by epsilon 0, it becomes 1. Then nq square by m divided by epsilon 0. That is why here you can see nq square by m epsilon 0 times sigma fj by omega j square minus omega square minus I gamma j omega. So we have the complex permittivity epsilon r tilde equal to 1 plus nq square by m epsilon 0 sigma j fj by omega j square minus omega square minus I gamma j omega. Now, in a dispersive medium, the wave equation is given by del square E tilde equal to epsilon tilde mu 0 dou square E by dou t square. And the solution of this wave equation is of the form E complex equal to E0 complex exponential I k tilde z minus omega t, where this k tilde, the complex wave vector, is square root of epsilon tilde mu 0 omega. We all know k is actually equal to root of mu 0 epsilon 0, I'm sorry, mu epsilon. K is equal to mu epsilon times omega. Okay, so this is equal to square root of is mu. Mu is equal to mu 0 times mu r, that is approximately equal to mu 0 itself. That is why this can be written as mu 0 times epsilon times omega. What is omega? Omega is the driving frequency of the electromagnetic wave. So we got the expression, the complex wave k tilde equal to root of epsilon tilde mu 0 omega, and this k tilde can be written as a real part and imaginary part. So k tilde is equal to the real part k plus I times kappa, the complex part. So therefore the solution can be written as, so substituting this into the expression solution, E tilde is equal to E0 tilde exponential I times, instead of k tilde we can write k plus I kappa z minus omega t. And we can expand this. This is equal to E0. You can write this as e to the power. There is an I outside and I inside. So I times I, it become minus 1. So e to the power minus kappa z. Then the remaining terms e to the power I k z minus omega t. Okay. So E tilde can be written as E0 e to the power minus kappa z e to the power I k z minus omega t. Now we know that intensity is proportional to the square of amplitude. So it is proportional to square of e to the power I k z also. This become minus 2 square of equal to minus 2 k z. It is actually E0 square times e to the power I 2 k z. So here you can see the term e to the power minus 2 kappa z, the exponentially decreasing term. This represents the absorption. We know that as the wave propagates through the medium, through this dielectric medium, its intensity decreases. That is signified, that is shown by the term exponential minus 2 kappa z. Okay, so we can write this as, or I is equal to E0 e to the power minus alpha z. This alpha is called the absorption coefficient. So comparing these two, we can write alpha is equal to 2 kappa. Alpha is equal to 2 kappa. This is absorption coefficient of the medium. Okay. Now refractive index. What is the expression for refractive index? N is equal to C divided by V. That is C divided by, what is V? It is omega, the frequency of electromagnetic wave divided by the wave vector k. So that is why N is equal to Ck over omega. N is equal to Ck over omega. Now 1 plus, so we have N equal to Ck over omega. K is actually the real part of the complex k tilde. So how to find that? Let us see. We know that k tilde equal to root of mu 0 times epsilon tilde omega. But what is epsilon? Is equal to epsilon r times epsilon 0, right? So we can plug in that here. This is equal to epsilon r times epsilon 0 times mu 0 times omega. But we know that c square equal to 1 by root of mu 0 epsilon 0. So what is mu 0 epsilon 0? It is 1 divided by c square. Now what is root of mu 0 epsilon 0? That is equal to 1 divided by c. So plugging that back here, you will get this is equal to root of epsilon r tilde times omega divided by c. Now, what is root of epsilon r? We already calculated epsilon r tilde. What is epsilon r tilde? That is this expression, 1 plus that one actually. Epsilon r is 1 plus nq square divided by m epsilon 0 sigma fj divided by omega j square minus omega square minus I gamma omega. This was the expression we derived for epsilon r tilde. Now, here it is square root of epsilon r times omega c. So when it's with the square root comes, it is the square root of epsilon r raised to 1 by 2 will come, and you can use the binomial expansion and its approximation to the first terms as the last term, as the higher order terms are can be neglected. So I hope you know 1 plus x to the power m is equal to 1 plus mx, provided x is very much less than 1, or a plus x whole to the power m is equal to a plus mx when a is less, x is very much less than the first term m. The higher order terms can be neglected. So using that here, what is m? The power, it is 1 by 2. So that is why the expression become 1 plus nq square divided by 2m epsilon 0 sigma, then the fj divided by omega j square minus omega square minus I gamma omega. That is why this k tilde is written like this. Okay, I hope it is clear now. How we got this k tilde, that is omega by c times 1 plus nq square by 2m epsilon 0 times sigma fj by omega j square minus omega square minus I gamma j omega. So we got expression for k bar. Now, what is actually our aim is to find the refractive index expression, c by omega times k, and alpha, the absorption coefficient, is given by 2 times kappa. What are these two quantities? They are the, it is k complex is equal to k plus I kappa. Okay, so k, small k is the real part of this k tilde, and kappa is the imaginary part of the k tilde. So we have to find this real part k and imaginary part kappa to find the refractive index expression and the absorption coefficient expression. Okay. Now, how we already got the expression for the k tilde. So, how to obtain this real part and imaginary part? As using a simple math techniques that we already learned, the conjugate multiplication technique for real and imaginary part, or the complex numbers. I mean, we can write k complex equal to omega divided by c times 1 plus, or we can take the second term only. Then finally we'll come to this expression. Okay, that will be better. So fj sigma of fj divided by omega j square minus omega square minus I gamma j omega. This is our number. How to separate this into a real and imaginary part is the question. Okay, so I can multiply this with sigma, or sigma j fj divided by omega j square minus omega square minus I gamma j omega. This is like x plus I, or x, I mean x minus, this is like x minus I y. Okay, so what we can do is we can multiply, this is the term. Okay, we can multiply this with what? We can multiply with omega j square minus omega square plus I gamma j omega. Okay, so we multiplied with the complex conjugate, the bottom, and on the top also the same. So on the top also it become omega j square minus omega square plus I gamma j omega. Okay, what is the need for this procedure? So this procedure we are doing for separating the real and imaginary part of the complex notation. Okay. Okay, this will be sigma j fj omega j square minus omega square divided by, this is like a minus b into a plus b, so you can write this as omega j square minus omega square whole square minus I square gamma square omega square. I square is minus 1, so this becomes plus gamma j square omega square again plus, again it comes sigma j I gamma j omega divided by omega j square minus omega square whole square plus gamma j square omega square. Okay, now what we did is we separated this term into the real part. This is real, this is the imaginary part. So we separated these terms into real part and imaginary part. Now how can we write the complete term? K tilde equal to, we can write this as omega divided by c times 1 plus n q square divided by 2m epsilon 0 sigma j fj omega j square minus omega square divided by omega j square minus omega square whole square plus gamma j square omega square plus again n q square divided by 2m epsilon 0. There is an I here. Okay, sigma j gamma j. I forgot to put on fj here. Okay, this is an fj also there. Okay, fj gamma j omega divided by omega j square minus omega square whole square plus gamma j square omega square. Close the bracket. Okay, so now we got the expression for k tilde equal to omega by c 1 plus nq square by 2m epsilon 0 sigma j fj omega j square minus omega square divided by omega j square minus omega square whole square plus gamma square omega square plus I nq square by 2m epsilon 0 sigma fj gamma j omega j divided by omega j square minus omega square whole square plus gamma j square omega square. So you can see here omega by c times this I and q. So this is the imaginary part. Okay, this is imaginary part. What is that? Kappa. And the first two times omega by c into I'll use another color. Omega by c into this. This represents the real part. That is k, small k. Okay. So we wrote k tilde as k plus I kappa. And we got the expressions for this k and kappa. Okay. Now we can write the expression for refractive index and omega. So this is the expression for k. If we know the value of k, I think we can write n. What is n? N is equal to c k divided by omega. So when you write this, the omega by c, you can see k has got an omega by c. So that get cancelled. So what is remaining is 1 plus n q square divided by 2m epsilon 0 and the complete sigma j terms fj omega j minus omega j square minus omega square divided by omega j square minus omega square whole square plus gamma square omega square. This expression for n. Now from the comparison we know what is kappa. The complex part kappa is equal to omega by c I omega I no there's no I okay omega by c times n q square divided by 2m epsilon 0 sigma j fj gamma j omega divided by omega j square minus omega square whole square plus gamma square omega square. So using this we can find what is alpha. We know that alpha is equal to 2k, I mean 2 kappa. Alpha is equal to 2 kappa. So how can you find alpha from this expression? Multiply this expression with a 2 will give alpha. Okay, so this will be alpha. So alpha is equal to 2 times n q square omega square divided by alpha is equal to 2 omega by c, and there is one more omega here. So what you can write this as omega square. So this will be 2 omega square n q square divided by 2 m omega 0 c. Then the sigma terms fj gamma j divided by omega j square minus omega square whole square plus gamma square omega square. 2 gets cancelled. So the remaining term alpha is equal to omega square n q square by m epsilon 0 c times sigma fj gamma j divided by omega j square minus omega square whole square plus gamma square omega square. So we got the expression for n and c, the refractive index and absorption coefficient alpha. Now, after getting the expression for refractive index n and alpha, the absorption coefficient, now let us try to draw the graph between refractive index and frequency, and absorption coefficient and frequency. Okay, so I think it's better we draw a graph between n minus 1 and omega. And so what is n minus 1 from here? When you take 1 to this side, n minus 1 is equal to nq square divided by 2m epsilon 0 sigma fj divided by omega j square minus omega square. So when for a particular values of omega j, the graph between n minus 1 and omega is like this. You can see the graph between these two. And this is a special thing there. When omega equal to omega j, we know that when omega means the frequency of electromagnetic wave, and omega j is the natural frequency of oscillation of the electron. So when these two equal, that's it. We know that that situation as resonance. So at a resonance, you can see that the n minus 1 versus omega graph drops to 0 at a resonance. At the same time, you can see that the graph between absorption coefficient and omega increases to maximum at a resonance. So that shows at a resonance, the electrons vibrate with a maximum amplitude and the absorption is maximum at that frequency. Now, when you increase the frequency further, you can see that the graph extends to the other axis. We know that the refractive index increases with the increase in frequency. As the frequency increases, refractive index increases. But in the immediate neighborhood of the resonance or near the resonance, the refractive index drops sharply, as seen here. This behavior of change in refractive index near to the resonance is known as anomalous dispersion. So normally refractive index increases with the frequency, but in the immediate neighborhood of resonance, refractive index decreases sharply with frequency. This behavior is known as anomalous dispersion. And here the anomalous dispersion happens between the frequencies omega 1 and omega 2. And at that same time, we can see that absorption increases sharply. So near the resonance, absorption is also maximum. Now, let us rearrange the equation for a refractive index. We know that is n equal to 1 plus nq square by 2m epsilon 0 sigma fj by omega j square minus omega square. What we can do is 1 by omega j square minus omega square. By taking an omega j square common outside, this expression can be written as 1 by omega j square times 1 by 1 minus omega square divided by omega j square, all to the power 1. When you take that to the top, the to the power 1 become to the power minus 1. So it is 1 by omega j square times 1 minus omega square by omega j square to the power minus 1. And applying binomial expansion and taking the lower powered terms only, 1 minus omega square by omega j square can be written as 1 plus omega square by omega j square. So putting this into the equation for refractive index, n equal to 1 plus nq square by 2m epsilon 0 fj divided by omega j square plus nq square by 2m epsilon 0 fj square or fj divided by omega j to the power 4. There is an omega j outside, and there is, so this omega j square that become omega j to the power 4. So this equation, this is very much equivalent to saying n equal to 1 plus, you can take some factors outside. N is common factor, nq square divided by 2m epsilon 0. There are the common factors there. Then omega j square is a common factor, right? What is remaining is, oh yeah, sigma fj is also a common factor. 1 plus omega square divided by omega j square. This will be the term that you are getting. Now we can write omega j. Omega j, it is 2 pi by 2 pi c by lambda. Omega j is 2 pi c by lambda j. Or we can write this like n equal to 1 plus, let this entire term be a. And the next term, there is an omega. Omega we can write 2 pi c divided by lambda. So this can be written as omega square is there, right? So this is a plus, or a plus, or we can write it as, okay, it is n q square by 2m epsilon 0 sigma fj divided by omega j square plus, instead of this, okay, there's the terms are there, n is there, q square is there, 2m epsilon 0 sigma j j divided by omega j square. Let that terms be there. Then there is an omega square on the top, and there is a remaining omega j to the power 2 also. So omega is 2 pi c. So we can write this as square is 4 pi c square divided by lambda square. Then there is an omega j to the power omega j square is remaining. Okay, so we can see that this term, then again that term like this. So now we can write this as n equal to 1 plus this nq square by 2m epsilon 0 sigma fj by omega j square is a common factor. So that is a times the remaining here is again 1 plus, then there is a 1 by lambda square the term. So 1 by lambda square. What all things are remaining there? That be the b value. So it be 4 pi square 4 pi square c square divided by omega j square. Let that be the b. Okay, so we got an expression n equal to 1 plus a into 1 plus b by lambda square, and this shows refractive index is inversely proportional to the wavelength. More the wavelength, less will be the refractive index. Okay, so less refractive index means more speed. So we know that red has got larger wavelength compared to violet. So the refractive index of red is less, so it travels faster. So bending is less for refractive index in a dispersive medium. So this equation is called Cauchy's equation. Cauchy's dispersion equation. And A and B, they're actually called Cauchy's constants. Uh, the constants A and B are called Cauchy's constant. The first one, A, is called coefficient of refraction, and the second term, B, is called coefficient of dispersion. The term A is coefficient of refraction, and the term B is coefficient of dispersion. Okay, so here we discussed the dispersion of electromagnetic wave when it propagates through a non-conducting or a dielectric medium. Next, we will discuss about propagation of electromagnetic wave through conductors. Next we have to learn about dispersion of electromagnetic waves in conductors and plasma medium. We all know that when we compare with dielectrics, conductors consist of large number of free electrons. They are not bound. The electrons are not bound to the nucleus as in the case of a dielectric. We learned about dielectric that they are bound, and so we used a model of a spring or a mass attached to a spring. So that model, a simple harmonic oscillator model, is used for the case of dielectric. But here, as the electrons are not bound to the nucleus, um, there is no bound oscillations of the electrons. So the resonant frequency omega j can be 0 in this case, as 0. And we can approximate the damping values also to very less or practically 0. So then this equation will reduce to epsilon r equal to 1. Actually, this is 1 plus nq square by m epsilon 0 sigma fj by minus omega square minus I gamma. So there is omega j becomes 0 and gamma j 0. So there is a minus omega square only. So that is why this becomes 1 minus nq square by m epsilon 0 sigma j fj by omega square. So now let us substitute nq square divided by m epsilon 0 as omega p square. This gives the expression for epsilon r equal to, or omega p square is nq square by m epsilon 0. Substituting this, we'll get epsilon r equal to 1 minus omega p square divided by omega square, where omega p square is nq square by m epsilon 0. Now, if omega, the frequency of incident electromagnetic wave, is greater than this omega p, then epsilon r will be greater than 0, a positive value. And we know that the wave propagation vector k is omega by c times square root of epsilon r. Since epsilon r is positive, there is no imaginary part, it's only real part. So therefore, this is the region of propagation of wave. And if the frequency of incident wave is less than omega p, then epsilon r will be negative or less than 0. That gives k, the complex k will be a pure imaginary number because of this root of negative number. It's a region of attenuation. Well, it is again, we deduce expression for relative permittivity, epsilon r is equal to 1 minus omega p square by omega square. But we already know that n is equal to square root of epsilon r. So n square is epsilon r. Okay. So n square, instead of epsilon r, we can plug in n square. So n square equal to 1 minus omega p square by omega square. We also know that n equal to c divided by v. But what is v? It is omega by k. So that is n equal to c k divided by omega. Squaring this, you will get n square equal to c square k square by omega square. So you can plug this in the equation n square in place of n square. You can substitute this c square k square divided by omega square equal to omega square minus omega p square divided by omega square. Omega square cancels. So remains is omega square equal to omega p square plus c square k square. Okay. So we derive the expression for omega square. This is a simple relation between omega and omega p and k square. And when omega equal to omega p, it is actually called longitudinal plasma oscillations. Okay. So, students, through this video module, we have learned about the dispersion relation of electromagnetic wave in dielectric medium and conducting medium and plasma medium. I hope this is clear. Thank you, students.